Hello everyone. In the previous sessions, we have learned the possible causes for the building's failure due to the improper soil investigation. Now, let us continue our learning journey and see what are the possible causes for the building's failure due to inadequate structural design. What is inadequate structural design? When the engineering fails, especially in the construction industry. Structural design. When engineering can fail. For any building structure or infrastructural facility, structural design begins after conceptualization, planning, and soil exploration. What is structural design? Structural design is the engineering stage that turns plans into a safe, buildable structure. It defines how the structure performs under real world loads and conditions. What is the goal of design? The goal of design is to deliver safety throughout the structure's intended life, withstand normal loads, deformations, misuse, and fire, ensure durability through standards, workmanship, maintenance, and use. What are the key structural components in a building? Basically, the building is a framework consisting of columns, beams, and slab, which are in turn connected by the foundation, which is below the ground level. What are the root causes? The invisible saboteurs. Structural failure rarely announces itself in advance. The most dangerous threats embedded in decisions made long before long before structure is ever occupied. Now let us see what are the basic mistakes that can happen in the structural design. Design errors. The entire design includes the primitive part is calculation of the loads coming on the structure. No. Now if the calculations are flawed or structural analysis that weakens the system from the outset. Human factors. Construction is mostly human dependent also because the construction is carried at the site of construction with the human labor involved maximum up to 80%. Now, when the human factors are there, poor workmanship or weak oversight that introduces critical defects during construction. Materials failure. Materials are the important things in the civil construction. The most important materials are steel and concrete. Now, if the steel and concrete failures, how it happens? Substandard or decayed components that cannot reliably carry the intended loads. Systemic neglect. Lack of maintenance and oversight that lets minor defects become major hazards. Each of these failure modes can exist independently, but when combined, they create a cascade of risk that is nearly impossible to recover from. Now, one case study which happened in US, the Hyatt Regency Walkway in 1981. The Hyatt Regency Walkway collapse in Kansas City remains one of the deadliest structural failures in US history, claiming 114 lives. A single design modification, changing rod configuration, doubled the load on critical support bolts, turning a safe design into a lethal one. The change, design modification, doubled the load on critical support bolts without adequate review or recalculation of the new load path. The outcome is structural collapse due to too many shifts and poor communication between fabricator, engineer, and contractor. A textbook case of coordination failure. Case study. One more case study is the John Hancock Tower, which happened in 71 till 76. This is basically $175 million engineering embarrassment. Boston's iconic John Hancock Tower became a symbol of what can go wrong when design assumptions fail to account for real world conditions. Key features are two distinct engineering failures plagued the lower throughout its early years, each revealing critical gaps in design methodology, foundation, and cladding. The reality is there was a $175 million engineering embarrassment, one of the costliest structural remediation projects of its era, with consequences spanning years. The failures are foundation shoring give way to clay settlement. Foundation shoring give way to clay settlement. 500 lb glass panes detached in wind. A dramatic and public demonstration of inadequate design verification. Environmental forces. Forces of nature versus structural weakness. Natural forces expose the limits of structural design. When engineering does not account for dynamic loads, the results can be catastrophic. Resonance. Tacoma Narrows Bridge. Collapse due to wind induced vibrations. Aeroelastic flutter destroyed the bridge in 1940, fundamentally changing how engineers design for dynamic wind loads. Seismic vulnerability, Turkey 2023. The earthquake exposed thin columns and lack of shear walls in thousands of buildings, a systematic failure of code enforcement and design standards. Common failure modes. Understanding how structures fail is the first step towards preventing failure. Each mode has distinct causes, warning signs, and prevention strategies. Axial. The axial forces are basically tension, compression, and buckling. Failures along the member's longitudinal axis. Bending and shear. Improper beam depth or the bolt failure under transverse loads and shear forces. What are the environmental causes? Corrosion, thermal movement, and cyclic fatigue that degrade materials over time. Combined multiple failure modes acting simultaneously, often the most dangerous scenario. Consequences. The hidden cost. Structural failures extends far beyond the physical damage. The ripple effects on economics, law, and reputation can persist for decades. Economic, massive repair costs and project delays that can bankrupt the developers and strain public budgets. Legal, liability for catastrophic property damage and loss of life, often resulting in multi year litigation. Reputational. Total loss of trust in engineering firms and contractors, destroying careers and company legacies. Human. Injuries and fatalities that are entirely preventable with proper design, materials, and oversight. Breaking the cycle of failure. Every structural failure is a lesson to be learned. The question is whether the industry learns before or after the next catastrophe. Rigorous peer review, coordinated design practices, and independent review at every stage catch errors before they become embedded in construction. Daily site supervision. Professional oversight of construction sites ensures that design intent is faithfully executed in the field. Certified materials. Mandating certified materials and regular long term maintenance prevents degradation from becoming disaster. Continuous education, ongoing training in failure analysis, code updates, and emerging materials keeps engineers at the forefront of safety. Prevention is always less costly financially, legally, and humanly than remediation after a failure occurs. Engineering ethics, a call for engineering integrity. Structures are a legacy of public safety, not short term savings. The built environment is a covenant between engineers and the public. Every beam, column, and connection represents a promise that people will be safe. Every beam, column, and connection represents a promise that people will be safe. Collaborative oversight. Success depends on collaborative oversight and ethical engineering standards across all disciplines and project phases. Code and accountability. Adherence to building codes is a minimum. True integrity means designing beyond minimums when lives are at stake. Code and accountability. Adherence to building codes is the minimum thing you can do. But true integrity means designing beyond minimums when lives are at stake. Building for the future. Prioritize structural reliability over convenience. The structures we build today will outlast us, make them worthy of that responsibility. Inadequate structural design is not an accident. Choose integrity, choose rigor, and choose the safety of every person who will ever walk beneath your work. Thank you all for being here. In the coming sessions, we will further explore the causes and consequences for the building failure. Keep watching the space. Thank you once again.